how to do this investigation now. It's just very similar to last time. So let's see if we can do it without spending too much time. In a way, we do exactly the same as last time. Last time we did this decomposition of the overall variability into those two things that we just discussed in the picture, the between group variability and the within group variability, right? And we made explicit that everything could be sort of expressed by looking at those two. Now between group, that's between treatments. Now that's a one-way table. When I have a two-way table, I can do between treatments and then I can do between blocks. Or maybe I should say between blocks and between treatments, depending on how you made your table. And basically we do two different between treatment variabilities, and we call it sum of squares for treatment, that's the one way of the table, and then sum of squares for blocks, that's the other way of the table. And as you can see, what I decide to actually call treatment and call block doesn't really matter anything. In all the computations, what we do here is completely symmetric in the two ways of the table. It's just a matter of what we call the main thing of interest. But we'll actually see sometimes they can maybe be more or less play the similar role of interest, actually, both of those ways. So we have the two between group variabilities, and then we have what is left, the residual variability. And then we can do everything. I've said that already. I think I have formulas here. Just to recap, total variability. That's the same as for one way. That's in a way same as what you were taught on day one in this course. I have a bunch of data. Let me forget all about those coming in groups and blocks or whatever. It's just a pool of data, and I could take all these data if it's a one column in my Excel sheet. Forget about all the grouping. I take the one column. I could compute the variance of those data, right? Ignoring all about group membership. I could just skip dividing by n minus 1 when I do the variance. So I just do the sum of squares. I don't divide by anything. Then I have what is called the sum of the total sum of squares. That's the total variability. That's the total amount of information in a data set. That splits up into, and now I gave you slightly different versions, but it's in a way exactly the same formula as last time. I'm just making explicit that my treatment sum of squares actually takes those individual treatment mean deviations and square them and add them up and multiply by how many blocks did I actually have for each treatment. And the other way around, exactly the same formula, but in the other way of the table. I take all the block deviations, I square them, I add them up, and I multiply by the number of treatment levels. And then the residual sum of squares, the rest, could be expressed like this, exactly like the residuals of a linear regression model, that it takes the raw data and it subtracts the predicted, the fitted, the estimated values of the model. That's the residual variability. Oh, we're going fast. Concentrate. Okay, you're doing well. I didn't even teach you this output yet, and still you got the point, most of you, which is good. Here you for the first time see an output from a two-way ANOVA. It's very much like the output from one-way ANOVA. There's just one more row. And I hope you could remember that you saw something similar when we moved from simple linear regression to multiple linear regression. We could have two, we could even in multiple have more rows. And if we are going to answer very rapidly about what is significant, what is not significant, we zoom in right away on the p-value column and we see two very small p-values here, right? So, and then we just have to remember what that means then, having small p-values. And of course it can be challenging enough. But it means exactly as most of you answered, that it means on both that the means are different, right? We reject hypothesis of equal means by seeing that we have very small p-values. So the means are proved to be different. We don't know anything about homogeneity of variance. And actually, I was fooling myself a little bit. I was seeing the blue as if you were right. You're actually doing less good than I thought for a second ago. So actually, you suck. No, you're okay, actually. Don't worry. Most of you. I didn't say that. Well, they can't fire me. I just had a new job. So I'll get back to that later. Rest in peace. Theory is doing well. Yeah.